Okay. So today we're going to take a look at 5.1. Okay, 5.1 is the beginning of chapter 5, but we'll find as we go through the chapter that 4.10, which we did on Monday, sort of flows very well with the rest of chapter 5. Okay, and so we're going to start today with what we know. So what do we know? We know position, velocity, acceleration. We've talked about those quite a bit in this course. But in particular, if we look at a velocity graph, can someone tell me what the y values of a velocity graph indicate? Yeah, the y values on v of t are velocity. Yeah, exactly. Okay. And can someone else maybe tell me what the slope on velocity tells us? Exactly. Perfect. No question mark, Thea. You are absolutely correct. It is acceleration. So the slope on velocity is acceleration. Okay. Okay. So these are things that we've looked at before. And so what's new? Okay. Maybe that velocity graph is something that we're like, ooh, we wish that would go away because it's weird and hard to read. But we're going to spend a little bit more time on that velocity graph, okay? And hopefully it will make a little bit more sense as we kind of come at it from a different angle, okay? So what's new today? We're going to be looking at the area underneath a velocity graph, okay? And this is going to lead us to a very big question that we're going to spend basically all of this chapter and part of chapter 6 talking about, which is how do we find the area between a curve and the x-axis? Okay, so we're putting on pause the idea of slope, and we're really focusing on area for the next chapter, okay? And so bringing back to our notes, all right? Today, instead of sort of writing down formal notes on the concept, there is an activity on Desmos that we're going to be working on together, okay? So this is part of the gradual release model that I sort of have as an educator, which is that at the beginning of the semester, the beginning of a course, there's a little bit more hand-holding, providing notes, things like that, okay? And I think those are all important things. And once in a while, I think it's important to practice our own ability to sort of take notes as we go through an activity, like what's important and what's not important, okay? So we will go through the Desmos activity together. However, you will be responsible for taking your own notes as we go through the activity. Okay. I just want to make that very clear before we start so that you're prepared. If you want to grab a notebook or whatever it is, that would probably be a good idea to have something to sort of jot some notes down on. Okay. Just to kind of preview what the rest of this will look like after we go through that activity. One important question we're going to be asking ourselves today is whether something is an underestimate or an overestimate, okay? And then we will spend the rest of time practicing, and I believe there are 2 different questions that we're going to be looking at, okay? So we'll have a chance to practice. We'll have a chance to explore the idea of over versus underestimate. But before we get to that, we're going to take a look at a Desmos activity, and we will work through that together. All right, so if I can, while I'm stopping my screen sharing and re-sharing with the Desmos activity, if you can all sign in to, well, let's sing, sign in to your Desmos account, all right? And if you go to our class, there should be an assignment that is called, what did I call it? Approximating area launch. Okay. So I'm going to stop sharing this screen. All right. So hopefully you have signed into your Desmos account. I'll give you a moment to do that. And if you can't find that activity, please let me know. But I see that 18 of you have signed on already. 19 of you have signed on. So I'll give folks maybe just a few more minutes to find that. All right, and as you've signed on, you are welcome to start answering questions as you like. You're always welcome to work ahead. Though if you have a question about something that is ahead, I may not address it until we all get there. All right, it looks like about 23 of us have made it on there. 24, this is good, this is good. 25. All right, let's just maybe give folks like 30 more seconds and then we'll take a look at this. All right, so let's begin. It looks like most of us have signed on. Again, this part will be recorded. I just won't be writing any notes on it. So whatever you write in the Desmos might actually be a really good way to sort of save any thoughts that you have as we go along, okay? So let's begin with this first slide. So how far did the ship travel? In this next chapter, we will study the concept of finding area under a curve. Now, we have seen that a physicist studying motion might want to look at slopes of curves, that is, velocity and acceleration. But what is it about those same problems that actually have to do with area under the curve? And that's really what we're going to be working on in the next 2 units, okay? So consider this problem. A ship moves along an ocean at a steady rate of 7.5 nautical miles per hour. We call that knots, okay? So if someone is going 7.5 knots, they are going 7.5 nautical miles per hour. And that ship is traveling from 7 a.m. to 9 a.m. What is the total distance traveled by the ship? All right, so I see a fair number of you have already answered that. But what do we get? How far did this ship travel?
15 knots.
15. Okay, I would say I like the number 15. Okay, and I think we got it from 2 times 7.5. But It's not knots because knots refers to the speed, and it's not quite miles either. We would have to specify nautical miles. Okay, so nautical miles meaning miles along, like when you're in the water versus when you're on land. Okay, so 15 nautical miles, that is the total distance traveled by the ship. And you can share that response with the class once you have that. All right. Are there any questions about how we got 15 nautical miles? Still see a few of you have not quite typed that in yet, so I'm still waiting on a few. All right. And if you are good to move on, maybe give me a thumbs up in the, that's one of the things that you can do in Zoom. All right, I see some thumbs up. This is excellent. This is excellent. Okay. All right, so let's move on to slide 2 then. So distance visualized as area. And so in this one, you're going to actually interact with this slide, and it gives you directions. It says drag point X from 7 a.m. to 9 a.m. And so here's my point X down here. And if I go ahead and hover my mouse over that, I'll notice that this cross hatch comes up. And if I click it and drag it, you should start to see something like this. Okay. Is everybody seeing that on theirs? It looks like people are. I don't want to go to 8, right? I want to go all the way to 9. And when I go all the way to 9, let's see, this is the graph of velocity. And on the bottom, I have hours. So let's read over this. You might notice that the distance traveled by the ship is exactly the area of this purple rectangle. Right? If we were to find the area of this purple rectangle, we would have base, which is 2, times height, which is 7.5. And we know that 2 times 7.5 gives us 15. Okay. Now, this is not a coincidence, all right? This is not an accident, because when we find the area under here, we're actually also finding the distance because we have time and velocity. Okay. Does that make sense to folks? All right, I have a few thumbs up here. Yes, yes. All right. Cool, cool. So let's change it up a little bit. Rectangles, we know. Squares, we know. But what about this one? All right, what if the ship had a velocity that actually changed over time? So it wasn't constant the whole time, but it looks like they were traveling like maybe around 6 miles per hour, and then they slowed down to 5 miles an hour, then they slow down to maybe 4.5 miles an hour, and then they speed up again. So it's not constant anymore. And if we think about dragging this point, right, from 7 all the way to 9, what do we think? All right, so there's no place for you to type in an answer, but maybe send me a private message that says whether a yes or no. Yes, you think this area of the irregular region still holds, that it's going to give us the total distance traveled, or no, you don't think it's going to give us the total distance traveled. Nice. Nice, nice. Okay. So I see a few people who say, yes, it will. And then I see a few people who say, no, it's not going to give us the distance travel. Okay. So if we think about a formula, maybe we knew once upon a time, distance equals velocity times time. Okay. That might ring a bell from like maybe high school science class or college science class, depending on what your most recent memory of science is. That distance is velocity times time. And when we're looking at this purple shape, even though it's not a rectangle anymore, this purple shaded area is in fact the area. It's the area. It will also give the total distance. Okay. Exactly, exactly. All right. So let's take a look at slide 4. Okay, let's take a look at slide 4. Over the first 2 hours, okay, the rate of snowfall. So we're looking at a totally different scenario now. We're leaving our ship behind and we're looking at a snowstorm, which I know for us is like, might be a really weird thing to think about since it doesn't really snow in San Diego. You can think about it like a rainstorm if you want. But when snow starts to fall, okay, it's starting at 3 p.m. And let's sort of read through this. It says, over the first 2 hours, the rate of snowfall increases from 0 to 1.2 inches per hour. So if we were sitting at our window watching the snowfall, what could we describe about that snowfall outside? Like, is the snow falling at the same rate? Is it getting slower? Is it getting faster? What do we know about that snow?
The first 2 hours, there's like nothing happening.
Okay. And from 3 to 5 hours, do you think the snow gets heavier or it stays the same? Good, good. Yeah. And so in this case, we see sort of the line goes up like that. Okay. Then this line represents the rate of snowfall. So as this line goes up, what we're looking at is a heavier snowfall. Okay. So maybe we see a few snowflakes in the beginning, and then after 2 hours, it's snowing pretty hard. Okay. Now, what about this next piece? For the next 3 hours, it continues to fall at 1.2 inches per hour. So let's say you are just sitting at that window watching the snowfall. Yes, Laura, I think that's a great descriptor. It becomes steady. So the snow is heavy, but it's coming down at about the same rate. In fact, it's coming down at 1.2 inches per hour all the way until 8 p.m. Okay. Yeah, there we go. I know what you meant. All right. Now at 8 p.m., it begins to taper off at a steady rate until 10:30. And so when we say taper off, that means that we are starting to slow down. And so if we were sitting by that window, we might see that the snow starts to get lighter and lighter and lighter until what time does the snow stop? Yeah, the snow stops like right around 10:30. Okay. Now, if you lived on the East Coast or anywhere where it snowed, this was like the worst time for a snowstorm because you finish school and then it starts to snow, but it stops before you go to bed, which means you're probably not going to get a snow day the next day. Probably have to dig your car out or whatever it is so that you can get to school the next day. I know. All right. However, if this was like 3 a.m. to 10:30 a.m., you would probably have a snow day in your pocket right there. Okay. So you see this, let's go back again one more time. All right. So you can go back to this again on your own time, but envisioning that the snow starts, it gets heavier, 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 and then it falls at a constant rate. And then it starts to slow down. Okay. So that's really what I want us to visualize as we're looking at a velocity graph. Yeah, if there was like heavy snow, you probably had an early dismissal. You probably got to go home before it got too bad. But I think sometimes those school buses, like being on a school bus in a snowstorm, is kind of scary. All right, but the question here, all right, find the total amount of snow that falls during this snowstorm. Use the graph to the left if you need any help, and enter your answer below, and then choose the correct answer or the correct units for the area. Okay, so we want to find the area of this blue part. Let's throw out some ideas here. What do we have in terms of how we can find the area for this blue part? Yes, so if you read what Laura's saying, she said, we're finding the area of the trapezoid.
I usually like to split it up into like 3 shapes. So there's like 2 triangles and then 1 rectangle, and then you find the area of each of those. Or never mind. I thought the 2 triangles were maybe like the same triangle, and you can just. Are they?
Since 3 to 5 and 8 to 10:30-ish are diagonal that just means it's half the area of the total places taking up. So we would divide it up into 3, like Nat was saying, in my opinion. So 3 to 5 would be it's 2 hours, but half of 2 is 1. So we would do 1 times 1.2 plus we have the steady snowfall from 5 to 8. So that's 3 hours. We would do plus 3 times 1.2. So we're at 4 times 1.2. And 8 to 10:30 is 3.5 hours. So 1.75 times 1.2. And the total of all of that is going to be the area. So the amount of snow that we have.
Okay. All right, so I love that, where we sort of break it up like we moved our cursor. So we could find the area of this blue triangle, right? And then we would find the area of this blue rectangle, like just the rectangle from 5 to 8. And then we would find the area of this triangle piece at the end. Okay, totally valid. If you've chosen that, go ahead and work through that. But alternatively, there is a trapezoid formula. And with the trapezoid formula, that is something that I think we tend to shy away from because we knew we could always break it into 2 triangles and a rectangle. But I think it's actually a valuable formula for us to think about, particularly in today's unit, where we're going to be looking at different ways of approximating things. And yes, so Laura has so kindly put the area formula for the trapezoid in the chat. All right. And so the capital A, I think, refers to area of the trapezoid. All right. Little a, don't auto correct it. Little a. It does autocorrect everything, huh? Little a is the length of one base, and little b is the length of the second base. Okay. So if we were to use that formula, just to kind of practice using it, can someone tell me what the height of the trapezoid is in this particular picture? What is the height of our trapezoid?
1.2.
Yes, I would agree that the height is 1.2. Okay, what about, let's say little a in terms of the length of one of the bases? What could we say that is? If you're using the top face, let's just make sure we count correctly. How long is that? Yeah, little a I would say is 3 if you want that to be the top. Okay. And then if little a is 3, then how big is little b? What is the length of little b? Yeah, I think 7.5, right? 7.5. Okay, great. So we'll plug those into your area equation. So it is 1/2 a plus b times h. So the only thing in the denominator is actually that 2. Okay, so you can take your a and your b, add them up, multiply it by your height, and then divide everything by 2. And let's see, what do we get when we do that? 3, 5. I'm getting 6.3. Is anybody else getting 6.3? Yes, okay, great. So here we can type in 6.3. Good job. Excellent. I love it when things give us feedback. And what are our units, right? What did we find 6.3 to be? Okay, I love it. I love it. Okay, 6.3. Exactly. 6.3 represents the amount of snow. Let's go total amount of snow that falls from 3 p.m. to 10:30 p.m. Okay, so therefore the units should be inches. Okay, does that make sense to folks? You can give me a quick thumbs up in there if yes, otherwise I don't know if there's a thumbs down option. There should be. Yay, cool, cool. Okay. All right, we ready to move on? We take a look at slide 5. Okay, so the rectangular approximation method, okay? Sometimes we call this, so rectangular approximation method is sometimes abbreviated RAM for rectangular approximation method, okay? But so when we have a function that is a curve, okay, we need a way, a consistent way to say, what's the area under that function, sort of, okay, approximately, what is it? And on the next two slides, or next few slides, what we're gonna focus on is 2 different methods, okay? And specifically, there is one called the left rectangular approximation method. Any guesses to the acronym that we tend to use for left rectangular approximation method? You got it. Yeah. So left, L for left, rectangular approximation method. And then there's additionally one that is called the right rectangular approximation method. And guesses to that acronym? There you go. Exactly. Exactly. Okay. So LRAM is your left approximation method. RAM, other LRAM. Well, there's going to be another one, Josh. So maybe that's not the best way to go. Okay. There'll be an other one then. But RAM, we're looking at the. I just typed that. That's not what you want. RAM is your right approximation method. Okay. All right, so we're going to take a look at sort of a left rectangular approximation and a right rectangular approximation. And we're going to find different values for our approximations. And we're also going to be considering sort of how many rectangles should we split things into, okay? So let's take a look at this slide right here, slide 6. Okay, so on slide 6, this is titled Approximating Area Using a Left Approximation Method. Okay, so what is a left approximation method? Well, this graph tells us, or shows us rather, what LRAM might look like. Okay, so how many rectangles do we have here right now? This is not a trick question. How many rectangles? We have 3 rectangles. Excellent, excellent. Okay, now for the 3 rectangles, do they have the same base or the same height? So if you compare the 3 rectangles, I know they all look different. They're sort of a short one, a middle one, and a tall one, but do they have the same base or the same height? Oh, okay. What is the base length for all of these rectangles? One. I love it. So good, so good. Okay, so in this case, we have that the base of each rectangle is 1. Okay. Now the heights are all different, right? But look at this region. So I've taken from 0 to, oops. I've taken it from 0 to 3, okay? And I took that distance and I cut it into 3 equal sections. And then, so in the first one, can I annotate on my own screen? Does anybody know the answer to that question? I think yes.
I believe so.
Okay.
Yeah.
Okay.
It's like view option, annotate.
Yeah. Okay, cool, cool. Okay, so notice from 0 to 1, okay, which number is on the left of that interval from 0 to 1? Like, is 0 the left side of that rectangle, or is 1 the left side of that rectangle? Yeah, 0 is the left side of that rectangle, right? So I'm going to put a little star here. Okay, so for this first rectangle, 0 is the left-hand number. Okay, and look at where the height of this rectangle is. I went to 0, which is the left-hand number, and I went up to the curve, and that y value became the height of my whole rectangle. Okay. So let's try this with the middle rectangle. The middle rectangle goes from 1 to 2. Which number represents the left-hand number in the interval 1 to 2? 1, good. So let's put a star here. Now let's check out the height of this rectangle. I went up until I hit the curve, and that y value right here became the height of the rectangle. Now, if I were to ask you about that last rectangle, which number, 2 or 3, is the left number, I believe that you would all tell me 2 is the left-hand number. And check out the height of this rectangle. I go at 2, I go all the way up to the curve. The curve tells me when to stop, and that becomes the height of the rectangle. Does that make sense to folks where these 3 rectangles came from? I've got 2 yeses. It would be important to hear more yeses, but only if you're genuinely feeling yes. Don't say yes because, you know, you feel pressured to. Okay. So I'm going to clear these annotations. Okay. So I'm going to clear these out. But now let's type in some different numbers. So this says enter several different values for the number of rectangles. So right now we have 3 rectangles. Right now we have 3 rectangles, okay? But what if we had 6 rectangles? What would that look like? I don't know if that'll draw it for me. Oh, I did. Okay, so now I have 6 rectangles here. And for each of these, if I annotate just a few of the rectangles, I know that from 0 to, what is this X value right here? The one that is the end of that first rectangle. What is that X value? Yeah, it's 1/2, okay? So 0 or 0.5, which one is on the left of that interval? 0, okay? This is the left. Check out the height of this rectangle. The height of this rectangle is the Y value at 0. Okay, well, let me skip a couple rectangles. Let's go to this 5th rectangle right here, the one that starts at 2 and goes to 2.5. Which one of those is on the left-hand side? 2 or 2.5? 2, okay. And the Y value, I go all the way up to the curve. I stop when I get to the curve. That Y value becomes the height of this rectangle. Right? And I could say the same thing for all of the rectangles, that the height of the rectangle is dictated by the left-hand Y value. Now, this is with 6 rectangles. Let me go back to 3 for a moment. Do you think that if I were looking for the area under the curve, so you see how I'm sort of missing this little triangle part up here and this little triangle and that little triangle, there's like pieces that I'm not counting, right? Do you think that 3 rectangles is better or 6 rectangles is better if I want to approximate the area? Yeah, 6 is probably better. Okay. Well, let me try another number. They've asked me to try 70. Let's see what that looks like. Whoa. That's a lot of rectangles. So we've tried 3, we've tried 6, we've tried 70. Which one of those do you think will give the best approximation? Okay, 70. And it says we could even do 3,000. I don't know, I haven't tried this one. Let's see, 3,000. What do we think? 3,000? Is it worth it to divide it into 3,000 rectangles? Like, does that look like an accurate area? Ah, it looks very accurate, right? It looks like a ton of lines. That is a great observation, Laura. It does look like a ton of lines. Okay. All right. So before we move on, let's take a look at 3 again. With 3, and I say, I want to find the area under the curve, and let me go ahead and maybe actually outline this area. So we're looking for the area that is, whoa, you folks are way better at this annotating than I am. Yeah, so this is the area in blue, right? This is the shape that I'm trying to find the area of. Do you think that if I only have 3 rectangles, will it be an over approximation or an under approximation? Okay, it would be under. Why is it going to be under? You are all correct. Yeah, we have blank spaces, right? What about this part? We didn't even talk about that. What about this part? We didn't even count that area. And what about that area? We didn't count any of those, right? So the area we get from 3 rectangles is going to be less than the actual values we'll get. Okay. All right. So you can come back and kind of play around with the number of rectangles, but the bigger the number that you put in, as Umar said, all right, the bigger the number of rectangles, the more accurate your approximation will be. Okay. All right, so let's move on. So this one is actually a little bit different. Okay, so this slide 7 looks at approximating area using a rectangular approximation, but that is specifically a right rectangular approximation. Okay, given the 3 rectangles right here, can someone describe to me how we know the height of each rectangle? How do we know the height of each rectangle? Okay, that is the question we want to think about. How do we know the height of each rectangle? All right, look at the y-axis, the right side height. We take the y value of the x of the right side, the y values of the curve. Excellent, so excellent. Okay, so I'm gonna do one annotation real quick. Let's use hearts this time, just because. So if I pick the middle rectangle, the interval goes from 1 to 2. 2, the number 2 is on the right-hand side of that interval. And so the height of this rectangle is going to be at the height or the y value of the x value on the right-hand side. Okay. Now, as folks are typing answers into the chat, these might be phrases that you want to write down for yourself when you're sort of thinking about taking notes, okay? But we've got all the heights of these rectangles are now dictated by the x value on the right-hand side, okay? So as long as you know your left and your right, fingers crossed, we should be good, okay? Now, do we think that if we make more rectangles, that it will then be a more accurate approximation? Like what Umar said about the left rectangular approximation, do you think that's also true for the right rectangular approximation? And if we're not sure, whoops, and if we're not sure, maybe we can try a few numbers. No more hearts. Go away. Okay, let's try 250. Let's see what 250 rectangles looks like. That looks pretty accurate. Lines, more than enough. Okay, what if we had 50 rectangles? Okay, that looks a lot better. All right. Now, that's a great observation. This is pretty good approximation. However, I don't know that I can zoom in for this. Do we see, like, if you look really close at the tops, we see sort of extra, almost like we've gotten, one might even call it an overestimate, right? And let's go back to the 3 for a moment. If we think about the area that we are trying to find, okay, the area that we are trying to find, we just want from here and down, well, we want this area. okay? So in this picture, if you looked at this picture and I said, do you think you have an overestimate or an underestimate? I would hope that every single one of you would say that we have an overestimate here because we've got more area, like all this extra up here, like this up here, that's extra, right? That's not actually underneath the curve. And this is extra. That's not under the curve. We don't want that. And this is extra also. Okay, so sometimes when we use one approximation versus the other, we'll get an underestimate or an overestimate. But in both cases, the more rectangles we use, the better our approximation will be. Okay. All right. But what about, all right, what if instead of having just a simple curve, we have an even more complicated function, okay? So maybe we have one that like goes below the x-axis, comes back up, goes back down for a tiny bit, and then shoots off into infinity, okay? Question one that I want us to think about. What about when this curve is underneath the x-axis? All right. So in other words, how does the blue area compare to the red area? This is not a political question, though we could have very many rich discussions about the current state of politics. But what does the blue area compared to the red area? Okay, so blue is negative and red is positive. Okay, let's maybe root this in the context of our problem here. Yeah, so the blue area, I would say, is considered negative area. Okay, negative because it is below the x-axis, all right? Whereas the red area is considered positive area because it is above the x-axis, okay? So let's imagine some numbers here, okay? Let's imagine some numbers. Let's say that this blue area down here is -5, and that's all right. So let's say that this area is -5. All right. What area do we want for this red bump, the first red bump that we see? Someone give me their favorite number. 7, +7. All right. And let's give this small blue bump a number as well. What number might we give to this small blue bump? Love it. Excellent, excellent. All right, and let's do one more. What could we put on this little red sort of triangle-y thing? Maybe a +3. Cool, cool, okay. All right, so we've got -5, +7, -2, +3, all right? So my question to you is how much, or what is the area between the curve and the x-axis from the blue dotted line to the end of the first red bump? Okay. And in other words, we're saying there are less color options here. From here to here, whoops, that's supposed to be a straight line. What is the area between those two yellow lines? Okay. What are our thoughts? I see a +2. Any other guesses? All right. Well, how did we get that +2? Maybe that's important part of the process to share with folks. Yeah, we took the area of the blue part, which was -5, and we added it to the area of the red part, which was +7, and that gave us +2. Good, very good. Okay. Once in a while, things in calculus are that straightforward. You can just add some numbers and get a number, okay? Now, what about if we said we wanted to find the area of this one and this one? How would we represent that? Maybe in terms of colors. Would we say red plus blue, red minus blue? What would we be thinking? Yeah, red plus blue. And so what did we say? The red area was +7. And then I think the blue area we said was plus -2. And so that would mean the area between the red bump and the small blue bump would be in total 5. Okay. How do we feel about that? Feel good, not good, mediocre? All right. So in this case, we put some numbers on it, but we got sort of the process that we would sort of add the red parts and then we would subtract the blue parts, or we would consider that the blue parts are negative, and that would give us the area, okay? So this is sort of the point of this, which is if we are clever, we can figure out a way to get a pretty good estimate of that area, okay? So how do we do this? Once upon a time, there was a man, last name Riemann. Okay, he is quite famous in the calculus world. You will often hear this phrase, not often, but you will occasionally hear this phrase, Riemann sums. Okay, Riemann sums. Now, Riemann sums really just mean find a bunch of rectangles. The more rectangles you have, the better your approximation will be. And if you have a whole bunch of rectangles, like you divide it into like 3,000 rectangles, you're going to get a pretty good approximation. Okay. So when you hear that name, Riemann sums, we're thinking that is the same concept as LRAM or RRAM, okay, where we divide the x-axis into a lot of equally sized rectangles. the y-axis tells you about the height of each rectangle. All right, so Riemann sum's just a fancy name for saying take this region, divide it into a bunch of rectangles, and use those rectangles, which we know the area of a rectangle is base times height, use that idea to find the area, okay? And so in this case, we have some rectangles here. Looking at the rectangles, and there's, I mean, I don't know that we have enough information for this to be right or wrong, but do we think this is going to be an overestimate or an underestimate? What are our thoughts? All right, and I heard a few folks who were saying maybe it could be both. It looks like this blue part here is like an overestimate and the red part is sort of like an underestimate, right? Do we think that the over and underestimates are going to cancel each other out in this case? Or do you think we have more of an overestimate and less of an under? Yeah, I think it's potentially, we could sort of make it maybe be more of an overestimate. It looks like these two pieces right up here, these three actually seem to be weighing heavily in that overestimate part, okay? But again, like if we have a picture, I think it makes it a little bit easier to tell, okay? All right, so let's take a look at this. This I will let you play around with on your own time, okay? But I just want to show you how it works. So when we look at the area approximation, see like all this symbol stuff down here, okay? We're going to worry a little bit less about the symbols, but this sort of pointy E looking thing is something called a sigma or a summation notation. Okay, it is a capital sigma. And that just means we're going to find each of the rectangles. And then when we want to add them all together, the sigma notation says, add up all the things you found. Okay. Now, notice in this picture right here, we've got one kind of approximation. We've got a left rectangular approximation. And we can check that it's a left approximation because look at this first blue rectangle, right? The left value is -1 and the height of the rectangle is dictated by that left-hand value. But if you want to see what the right-hand approximation looks like later on, you can go back, you can change this C value. So it says set C equal to 1 and you can see the area. So I'm going to take this, I'm going to drag this over to 1, and now I have a right approximation. Okay, so left approximation, right approximation. Left approximation, right approximation. Okay. Now, what you'll be able to look at on your own time is thinking about some other ways. All right, so this is the left, this is the right. But remember earlier, I think it was Josh said the other approximation, which is valid, but there's secretly a third one, which is the midpoint approximation. So you can use this to look at what happens if you choose the y value of the middle x value. Okay, so left, right, and middle. Okay, so I'll let you sort of finish that piece up on your own time. Okay, But I hope this was a helpful way to kind of walk through the Desmos activity. I know that sometimes it can feel really overwhelming when there's this activity and you're not really sure what patterns you're supposed to be looking for. So I hope that that was a little bit more helpful to kind of get walked through that together, okay? And you folks did a great job with the contributions in the chat. I thought that that was really awesome to just hear what everyone is thinking about things, okay? So we are definitely overdue for a break, all right? It is 10:45, so let's go ahead and take a 15-minute break. We'll come back at 11 a.m., okay? Oh yeah, but these geniuses, they found a way to cut it into different shapes as well. There's actually other kinds of approximations too that are pretty cool. All right, but I will see you folks back here at 11 a.m. Okay, so take a good stretch break and I'll see you back here. All right, so I know this was sort of a different style than we normally do. In the past, we've done some Desmos activities, either individually or in small groups, or maybe together as a whole class, but we've always sort of summarized things as we go. So again, this piece on sort of the note-taking piece, I tried to add some things into the chat so that you would have some things to write down, but it might be worth sort of going over that video again and just making sure that you understand sort of the concept behind that left and right hand approximation, okay? And so before we dive into that, let's kind of talk about this idea of over and under estimates, but in a visual sort of way. Okay, so if you haven't caught on by now, I'm very big on visuals. I think that it ties together a lot of the concepts that we're talking about, the calculations that we're getting, and sort of helps connect all of those pieces together. Okay. So let's take a look at sort of 4 different cases. Okay, so we're going to draw 4 different pictures in this case. And so let's assume that we had a x-axis, all right? For now, I think we'll not draw a y-axis because I don't think that it's necessarily relevant to the particular points that we're trying to get across, okay? And let's set up another x-axis over here. And let's get a picture of a graph, okay? So let's suppose that you have a graph that is increasing. And so you have a function that maybe looks like this, okay? Now, would you say that this is concave up or concave down? Okay, good. It is increasing and it is also concave up, okay? And in the picture next to it, I'm also going to draw an increasing function, but we're actually going to draw one that is increasing and concave down. And so that might look something more like this. Okay. Do we see how they're both increasing? Like both functions, the y values go up, but one of them is concave up and one of them is concave down. Okay. And now we're going to divide this. And for the sake of the diagrams, we're just going to divide it into, like, let's say 4 rectangles, 3 or 4 rectangles. Okay. So let's say that I had a few rectangles. So here's 1 rectangle. Here's 2 rectangles, and here's the 3rd rectangle, okay? And we do the same thing over here. We have sort of 1, 2, 3 rectangles, okay? Now notice I didn't draw the tops of the rectangles. I just drew sort of the vertical dividers between the rectangles, all right? Looking at the first picture, okay, so looking at the increasing and concave up picture, what are our guesses for if I used a left rectangular approximation versus a right rectangular approximation? Which one do you think would give you an overestimate, and which one do you think would give you an underestimate? Okay. So we're really thinking about those two questions. Does LRAM or RRAM give an overestimate? And does LRAM or RRAM give you an underestimate? Okay. All right, what are our thoughts? Do we agree with Graham that the left approximation will be an underestimate, whereas the right approximation will be an overestimate? Now, in the past, and by the past, I mean like 45 minutes ago, we had technology that was drawing this for us. But maybe I should have used a different color here. How would I draw the left approximation rectangles? Like, where would those lines be to draw the tops of my rectangle? Well, I could go back to the idea of like, look at an interval. So on this interval, I choose the left hand X value, and that Y value becomes the height of my rectangle. Everybody see how I did that with the LRAM? You can give me a quick thumbs up or a yes in the chat, or a no. That is also a fine answer. Okay. And so if I continue to draw these left rectangles, I think we would see that Graham is correct, that we've got an underestimate here. Okay, because we're sort of missing chunks. We don't get the whole area. But if we were to do the right rectangular approximation, we would actually get tops of rectangles that looked like this. And so I think we can see from there that we would get an overestimate. Because the green rectangles are above our curve, sort of those extra bits that I think Ethan had pointed out in one of our examples that we looked at. Okay. Well, let's take a look at this second diagram. I've got increasing and concave down. What are our thoughts? Which one's going to be an overestimate? Which one's going to be an underestimate? All right, so I see same. I don't know, let's draw a couple pictures and see. So left, left, left. That sure looks like an underestimate to me. And the right ones, oh, yep, there's extra. Okay, so it looks like it doesn't matter if it's concave up or concave down, but as long as we have an increasing function, Okay, as long as we have an increasing function, the left approximation will be an underestimate and the right approximation will be an overestimate. Okay. Now I'm going to set up 2 more diagrams, but I'm going to ask you to do these on your own time, where we're going to take a look at what happens if you have a decreasing function. Okay. And so we'll again split this into 2 cases, decreasing concave up and decreasing concave down. All right. And I'm even gonna not draw the diagrams because I think that's actually a really good exercise for you to kind of draw that picture, see what you get, make sure that you know how to draw something that is concave up and something that is concave down, and then figure out which one's the overestimate, which one's the underestimate, okay? So maybe put a star next to this in your notes as something to come back to as a thinking exercise. All right, so the moment we've been waiting for. What do problems that ask us about approximation actually look like? Okay, and so we're going to work through 2 examples. We're going to draw lots of pictures, and we're going to do mostly pictures and setting up of equations and not that much of actual computation. Okay, so in similar flavor to maybe what you might expect for the related rates or the optimization question on exam 3, more emphasis on the setup, more emphasis on I know why we're choosing these numbers, and less on can I type numbers correctly into a calculator. Okay. So let's take a look at this first example. So the speed of a runner increases steadily during the first 3 seconds of her race. Her speed at half-second intervals, excuse me, is given in the table below. Excuse me. So she's got her time and her seconds, so her time measured in seconds and her velocity, okay? And so what we're going to do first is we are going to plot the points on the grid below. Thank you. So we're going to plot these points, okay? And let's see what we get. We are not, however, connecting the points. So we're only plotting them, okay? So the first point I'm going to draw is going to be 0, 0, because we have at 0 seconds, her velocity is 0. Okay. And then we're going to go ahead and plot all the other ones. So at 0.5, she's going at 6 feet per second. At 1 second, she's going 10 feet per second. At 1.5 seconds, she is going at 15 feet per second. At 2, she's at 18 feet per second. 2.5, she's at 19. And at 3, she's at 20 feet per second. Okay. Now, based on this picture, would you say that her speed or her velocity is increasing or decreasing? Yeah, that's velocity is increasing, right? She started at a velocity of 0, she finishes at a velocity of 20, and we can see the points go up the whole way. Now, if we kind of compare this to what we just talked about with the over and under estimates, we would expect that if we chose a left approximation, we would get an underestimate. Whereas if we chose a right approximation, we would get an overestimate. Does that make sense? So increasing functions, the left approximation is going to be an underestimate and the right approximation will be an overestimate. Okay. So looking at our picture here, all right, we're not going to draw anything else on this picture for right now, but we can sort of see that if we were to draw more, that we would find that our left ones are going to be under and our right ones are going to be over. Okay. And so let's take a look at this first question here. Find LRAM using 6 rectangles. All right. So we're going to take this whole region between 0 and 3 on the x-axis, and I want you to split that up into 6 equal pieces. Is it increasing because it has a positive slope? Yes, that is one way to think about it, right? If you were to sort of visualize this trajectory, it has a positive slope, but also it's increasing simply because the y values get bigger and bigger. All right, so those are two sides of the same coin. It's increasing because it has a positive slope, but it's also increasing because the y values get bigger. Okay. All right, so let's take this region between 0 and 3. And if you were to cut that up into 6 equal bases for your rectangles, what would the length of each base be? 0.5. That is spot on. Okay, so we know that the base of each rectangle is 0.5. Okay. Now, one way that we could get this is kind of look at the picture and sort of see that from 0 to 3, if I count by a half, then I will get 6 equal lengths. All right, so like 1, 2, 3, 4. I'm going to choose a different color. So sorry. 1, 2, 3, 4, 5, 6. Right, I've made 6 equal pieces, and they are literally a half in length each. But how could I find this just from the equation? That's an important question to ask yourself. How do I find this if I don't have a picture? Well, what you can do is you can take the interval that you're looking at. Okay, so over the interval from A to B, all right? And you can say, I'm going to take the last number, which is 3. I'm going to subtract the first number, which is 0. Okay, so again, this is 3. This is 0. So I'm doing 3 minus 0. And then I want to take that distance and I want to cut it into 6 equal pieces. And look at what we get. 3 over 6, or 1/2. Okay. So one way to find that distance is to look at the picture and cut it up in your head and count how long each base is. The other way to do it is to use this formula. Okay, and we'll write out the general form of this formula. So in general, base equals b minus a over n. All right, b minus a over n, where b is the end of the whole interval, a is the beginning of the whole interval, and n is how many rectangles you want. Okay. Any questions how we found 1/2 or 0.5 as the length of the base? Okay. Now we got to find the height of each rectangle. Now the heights of the rectangles, I think we can tell they're all going to be different heights, right? We're going to have some taller ones up here. We're going to have some shorter ones down here and some even shorter ones down here. Okay, so the height of the rectangle changes. So how do we find that? Like let's look at this imaginary rectangle right here, okay? What is the left-hand x value there in this interval? What is the left-hand x value? Left-hand x value. Yeah, that left-hand x value is 1, right? Okay, but you're thinking like 2 steps ahead of me. What is the y value of that x value? And Josh was right, that y value is going to be 10. Okay, so if I were to draw that rectangle, I would have the heights of this, but the top of my rectangle would be measured by that left hand x value. Okay. Now I'm going to go ahead and draw all the other rectangles here. So I'm just going to divide them up first. So I'm dividing, all those bases are the same. And now, can someone tell me what the height of this last rectangle is? What is the height of that last rectangle? Is it 19? Is it 20? 19, yeah, because we're going to use the left-hand value. Okay, what is the height of the 5th rectangle, or this one right here? What is the height of that rectangle? 18, okay. Then the height of the 4th rectangle looks like it's going to be 15. The height of the 3rd one is 10. The height of the 2nd one is 6. And what's the height of the 1st rectangle? Yeah, it's 0. Weird, but it's true. It's 0. Okay. So if we were to imagine this curve that connects all the points that we have, I think we can see here that we're going to get an underestimate because there are chunks missing from the area. Okay. So we found the height of each rectangle, and let's list them out. 0, 6, 10, 15, 18, and 19. Okay, so 0, 6, 10, 15, 18, 19. Now, let's go back to our table for a moment. Where do we see those values? 0, 6, 10, 15, 18, 19. Where do we see those? Those are the velocity values. Okay, are they all of the velocity values? Like, did I just take every single velocity value in my table? I have a yes. Let's see. We've got 0. Whoops. We've got 0. We've got 6, 10, 15, 18, 19. Oh, but we don't have 20. Okay. This is actually an important sort of generalization here. If someone asks you to find the left approximation, one way you can think about it is you're going to use all of the y values except the last one. In other words, you pick the left x values. You do not pick the last one though, okay? So we use all of the left values, which means that we leave out the one at the very right. Okay. So how do we find the area? Well, we can multiply every single one, find each of the 6 areas. Okay. So what would that look like? The area would be, let's see, I'm going to use 1/2. 1/2 times 0, that's the area of the first triangle, first rectangle, plus 1/2 times 6, that's the area of the second rectangle. How would I write the area of the third rectangle? One half times 10, good. So 1/2 times 10 plus 1/2 times 15 plus 1/2 times 18 plus 1/2 times 19, but we don't include the 20 because that's not on the right, on the left-hand side. That is on the right-hand side, okay? Now you could sit and type this all into a calculator, that's fine and good, but let's be clever, all right? Let's be clever as mathematicians. What do you notice about every single term that we are adding together? In other words, what do all the terms have in common? Yeah, they all have a 1/2. So as mathematicians, we're going to say, I notice they all have a 1/2. And they all have a 1/2 because the base of every rectangle was 1/2. All right, that's why they all have the same, because we made them have all the same. And so because as mathematicians, we are trying to be as efficient as possible, we're actually going to factor out that common factor. Okay, so this is the 1/2 that is in every single one of these areas. And then we're just going to add up whatever's left. 0 plus 6 plus 10 plus 15 plus 18 plus 19. Okay. And you can type that out. You can find out what it equals. All right. But if we were to think about a formula in general for a left approximation, we might write it like this. Notice that the base is out in the front, and we said that the base could be found by b minus a over n. So in general, I'm going to put b minus a over n in the front because that is the base, and it's the same base for every single rectangle. And then I'm going to say f of, we're going to call this x sub 0. Okay, so x sub 0 just means the first x value plus f of the next one. And we're going to keep going until we get to, running out of room here. We're going to keep going until we get to f of x n minus 1. And this n minus 1, all that means is do not use the last, do not use the last y value. Okay, so that's what this means. You go all the way until you're almost at the end, but you do not use the last y value. Okay. Does it make sense to folks why we do not use that last y value for the left approximation? I've got one yes. It's okay to say no. You can send that to me privately if you wish. Okay. So let's maybe look at that picture again, right? So when we looked at the picture, we picked all of the left values. This one, this one, this one, this one, this one, and this one. But we only want the left values of each rectangle. If I chose this one, then that would be the right value of a rectangle. So that's why we leave that one out for the left approximation. Does that make a little bit more sense, Christina? Okay. And if we wanted to look from the table, we would choose this one, this one, this one, this one, this one, this one, this one. And we would leave out the last one because that would give us a right value. And we only want the left values. Okay. And yeah, Umar would almost assume that we have one more rectangle, but we're done. That's it. No more rectangles. Okay. So how many rectangles did I ask us to draw here, by the way? Not a trick question. How many rectangles are we drawing? We're drawing 6 rectangles. Okay. So if I want 6 rectangles, I'm going to need 6 y values or 6 heights. 1, 2, 3, 4, 5, 6. I only have 6 rectangles, so I better only have 6 heights. If I have more than 6 heights, then I have more than 6 rectangles. Right? So the number of heights that we have should match the number of rectangles we want. Okay. All right, well, we'll have a chance to kind of practice this reasoning again. When we look at the right rectangular approximation. Okay, so the only difference between B and C is that now I'm asking us to use the right rectangular approximation. Okay. Now, if I were to look at my table, okay, and I wanted to use a right rectangular approximation, which of the y values would I use and which would I not use? Because I have 7 y values altogether. And if it's helpful to you, you can maybe annotate on the screen, like what would it look like if we drew right rectangles? Okay, you folks phrased it really well when we were working with the Desmos activity of like, where does the height of the rectangle come from? So maybe we can use that as a tool here to help us figure out which Y values from the table we're going to use. Yeah, so the question is, which one of these Y values up here am I going to use for right rectangular approximation? Okay, so which one of these am I going to use for the right rectangular approximation? And if it's helpful, how might we draw these rectangles here? Yeah, excellent. There you go. Nice, 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 nice. Okay. Now, what I really appreciate here, and I'm going to go ahead and box this off as well, is that we're using all of these values to find a right rectangular approximation. Yes, exactly, Thea. We're going to use all of them except for the first one. Because check this out. We've got this as the height for the sixth one. This is the height for the fifth one. This is the height for the fourth one. This is the height for the third and the second and the first. And you know which one got left out? We didn't use that Y value of 0, which matches here. We didn't use that Y value of 0. Okay. So if we were to kind of overlap, I might say these ones are for the LRAM, whereas the ones in the green are from the RRAM. So purple is the left one, and then the green is the right one. Okay. So we don't use, okay. No, you're fine. We don't use 20 for the left one, correct? Because that is the last one. We do not want to use the last one. And we don't use the first one for the RRAM. Exactly. All right. And so that might not be something that I write down, but if that resonates for you, and I'm speaking to everyone here, that would be a really good thing to write down in terms of a pattern that we found. Okay. All right, but what does the equation part look like? Okay, so if we were to write out the area of our right approximation, we should have 6 rectangles again. So 1, 2, 3, 4, 5, 6 rectangles, okay? Now, every single rectangle will have a base of 1/2, and we know that because we made it that way. Now, let's think about the heights of each of the rectangles. So this first rectangle, is this height, would you say that is f of 0 or f of 0.5? Okay, let me ask that question one more time. Is this height f of 0 or f of 0.5? Yeah, f of 0.5, good. Okay, and so is this height, how could I describe that in terms of y values? F of 0.5 or f of 1? F of 1, good, good, good. Okay. So we're gonna say this is f of 1/2, f of 1, f of 1.5, f of 2, f of 2.5, f of 3. Now again, we might notice every single one has the same base. So that seems like a lot of wasted ink to write it again and again. So we might say in general, we could factor out that 1/2, and then we'll have all of the corresponding y values in there, which let's see, I think we get 6 plus 10 plus 15 plus 18 plus 19 plus 20. You can type that into your calculator, but this is fine to leave it like this. And we are using everything but the first y value. Okay. So let's see if we can get that all on one screen. All right. So I know this is sort of a lot to digest in terms of like drawing the pictures, using the tables, and like thinking which ones do we use and which ones do we not use. So if you're feeling still kind of like stuck on this, I think you'll find that that last quiz question gives you a little bit more practice in terms of how to draw these. So the base and the height are the same. I would say the base is the same. The base is the same for left and right because it's just the 1/2. But for each rectangle, the heights are different though. Like the height of this rectangle is 0 and the height of this rectangle is 6. Those are not the same, right? Yeah, but the bases, those are the same. Exactly, exactly. Okay. Now we're going to talk through one more approximation. And that one is the MRAM one. Okay. We do have the trapezoidal approximation here. We're not going to get to that, and that's totally fine. This is something that you can explore on your own if you wish. Okay, but you do not have to look at that trapezoidal approximation. Okay, so I'll make that modification. I think one of the quiz questions has a trapezoidal approximation. You don't need to do that one. Okay. But I'm going to grab the values real quick from my table above. So 0 and 6 and 10 and 15, 18, 19, and 20. All right. And now we're going to look at what it might be to find the MRAM. Okay, so M here stands for the mid point. That does not say point. The midpoint of each rectangle. Okay. So just like we have the left and the right, there's one that happens in the middle, and there's a good animation on that Desmos activity to help you figure that out. Okay. Now, if we were to draw these, okay, let's think first about how many rectangles we have here. So I want us this time to only divide this region into 3 rectangles. Okay, So where might I draw my dividers on the x-axis? Right, and let's get this picture on one screen here, but where would I draw the dividers so that I could have 3 rectangles that all had the same base? At 1 and 2. I agree almost that there should be a divider at 1 and a divider at 2, but maybe there are some more dividers that we need. Where might those other dividers need? 0 and 3. Yeah. What did I even just say? Where do those other dividers need to be is what I meant to say. 0 and 3, right? Because we got to close off that region. Okay. So earlier for the LRAM and the RRAM, I said there's a sort of a general formula you could use to find the base height or the base length. So for the base, that formula we said was B minus A over N. And if we plug in our numbers here, we get B, which is 3, minus A, which is 0, over N, which is the number of rectangles. And so the base of each rectangle should be 1. And if we look at our picture, this is 1, this is 1, and this is also 1. Okay. So we've got our bases, but to determine the height of each rectangle, this is where I'm interested to hear your thoughts. Let's start with this first rectangle right here. Okay, the one that goes from 0 to 1. What y value should I use? And which x value does it correspond to? And maybe the x value is the more important part. Yeah, we want to choose the point that is in the middle. Well, what's in the middle of 0 and 1 is 0.5. So this is going to be the height for that first rectangle. All right, so I'm going to say f of 0.5. Okay. What would we say is the height of the second rectangle in terms of the x value? Like f of what will give me the height of the second rectangle? Yeah, again, we choose the middle value, f of 1.5. That means if I draw this for the second rectangle, is that correct or incorrect? What do we think? Did I draw the right picture, the correct picture for that second rectangle? Okay, I say incorrect. All right, so what would I need to change then? What should the height of that rectangle be? It should be at 15. Good. So I'm going to sort of get rid of this line. We're going to go a little bit taller until we get to that 15. And there is that second rectangle height. All right. The last one should be f of 2.5. And so I'm going to go all the way up to f of 2.5, which is 19, and draw in that third rectangle. Okay. So if we want to find our area, we can set this up as, let's be clever. Let's pull that base out all the way to the front. 1 times f of 0.5 plus f of 1.5 plus f of 2.5. And I can grab each of those values from the table above. We get 6 plus 15 plus 19. That will be the approximation using MRAM if I have 3 rectangles. Okay. All right. How we doing out there? I think that it is not that I mean to have you be like, feel like you're unsupported in this, okay? And so I think this is a really good, if you're feeling like I kind of get it, but like extra practice would be helpful, that is a good place to feel a lot of times in sort of like upper level math classes, okay? And what that does mean then is that the sooner we can kind of get that practice in, and I know you all have very different or, busy schedules, but the sooner we can get that practice in, the more sticky it becomes in our brains, all right? Whereas if we sort of wait, even like, I think studies have shown, even if you wait like an hour or 2 hours after to sort of, go back and re-look at the notes, that your brain actually forgets a lot of that stuff within those first few hours. Okay. So if you have time, even just like 10-15 minutes after, to write down some notes for yourself, or think about like what aspects of this in particular you would like to practice, that can actually be really helpful for you. Sometimes when I'm taking notes in my own classes, I'll like put a big star next to something and be like, study this later, like come back to this. And so I'm sort of leaving myself a trail to come back to, so I know like what it is that I need to study. Okay. I would encourage you, yes, Paul's online notes has some great resources, but also thinking about like, there's a whole nother problem that we didn't get to here. That might be a great one to work through during tutoring or just in a small group. And if you are not sure about your answer, great chance to come to office hours on Friday or a different office hours and say, hey, I worked through example 2. I was wondering if I could just check my work with you and make sure that I'm reasoning through the question in the proper way. Okay, so if you're like, I never know what to ask in office hours, this is a great example of something you could say, I did this extra practice problem on my own time. Can we go over it to make sure I really got the concept? All right. So I think this is a good place to stop for today.